Well, after that introduction, thank you so much for that, Teri. I still call you Miss Bellows instead of Teri, but I'm not really sure what to say. That was the best pro con. The con is that now everyone's expecting a really, really good talk. The pro is that I couldn't possibly blush more than seeing grade school me wearing black socks with white sneakers. What was I thinking? But anywho, here we are. So if we're all set, we'll just go ahead and dive right in. So I've called this talk Mass Outflows in Active Galaxies Part 2. So a few years ago I was here and I was just at the very beginning of my research and I was just kind of talking about what I was going to be working on. And so I'm very excited today to be back and talk about kind of the conclusion to that. And of course I've kind of kept it in air quotes because there's never really an end. We answer some questions and we just find more. So with that, I'll go ahead and dive right in. I'm very excited to share this research that I worked on for my PhD. And so first I'd just like to go ahead and say thank you to everyone in my research group and everyone who I've worked with over the years, in particular my advisor, Dr. Mike Crenshaw from Georgia State University. He really took a lot of time to teach me everything that I needed to know in order to do this research. And then also all of my collaborators, and in particular I'd like to highlight at the top there Judy Schmidt. She is an amateur astronomer and world-class image processor, and she kindly produced many of the very stunning images that you're going to see today that I included in my dissertation and in my research. I also have to give a very special thanks to my family, to my wife, to my friends, and my teachers, many of whom are here today, and I'm very glad about that. And of course, the NJAA. So I think it would be the understatement of the night to not say that the NJAA was probably the most instrumental piece in me deciding to pursue a career in astronomy. So thank you very much to everyone here for their support. And then finally, I would just like to thank the National Science Foundation. When I was at Georgia State University, I had a graduate research fellowship, and that gave me the tools and resources that I needed to really accelerate the pace of my research and be able to share it with a much larger audience. So I was very, very fortunate for that. So with that, let's go ahead and just dive right into our science. Here we have some images of some spiral galaxies. On the left, we have what we call basically an edge-on spiral galaxy, and on the right, we have more of a face-on orientation. And so we can go ahead and highlight some of the key components of galaxies. So first we have the nucleus, and this is just the most center region of the galaxy. And this is where a lot of the activity is going to be going on that I'll be highlighting today. Then around the nucleus, we have the bulge. And so this is kind of a roughly spherical distribution of older stars that are all orbiting around the center of the galaxy. And they kind of form this spherical ball of stars that's somewhat distinct from the disk of the galaxy itself. And then after that, we have spiral arms. And so these are these beautiful spiral structures that we see in these galaxies. And these are regions that are slightly more dense. They have slightly more gas and dust. And because of that, they have lots of hot young stars that we see shining in these bright blue and white colors. And then somewhere, hidden down in the very center, is a supermassive black hole. So this is not to scale. These supermassive black holes are actually quite small compared to the size of the galaxy. So in general, we can't actually see them as a distinct entity. They're somewhere hidden down in the center of the galaxy. And everything that I'm going to be talking about today kind of ties into the relationship between supermassive black holes and their galaxies. So in order to get kind of the best first view of supermassive black holes, we can look no further than the center of our very own galaxy, look at the Milky Way galaxy. So when we do that, if we go ahead and point particular types of telescopes there, we can trace the motions of stars at the center of our galaxy over the course of about 20 years. And what we see is that all these stars are orbiting around this single point that's marked with a star. And when we point the majority of our telescopes there, we don't actually see anything. And so if you go ahead and look at these stars, look how fast they're moving, look how close they are to this very massive object, the only thing that we know that could hold those stars there is a supermassive black hole. So this is an object that is extremely dense, extremely compact. It might have a mass of millions or even billions of times larger than that of our own sun, but it's all crammed down into a volume about the size of the solar system. So it's an object that's so dense and so massive that even light cannot escape. And so in general, when we look at most galaxies, this is the picture we get. We just kind of have this indirect tracer that there's a supermassive black hole at the center of that galaxy. However, there's another class of galaxy that helps to shed some more light on things, and that's when we look at active galaxies, or active galactic nuclei. And so these are galaxies in which the central supermassive black hole is actively eating material, in particular gas, from the surrounding galaxy. And so here's kind of an artist's conception. We have this supermassive black hole, and we have material in what we call an accretion disk, and this material is being compressed and heated up as it falls into the gravitational potential of the supermassive black hole, and it emits an immense amount of energy, just in the form of light, in the form of photons. And this comes all across the electromagnetic spectrum, so very high energy X-rays through the optical down into the infrared and even in the radio. So we're basically getting an immense amount of energy coming from a very small volume. And the way that we quantify this amount of energy is through what we call the bolometric, or the total luminosity. So that's a term that I'll use a lot. It's basically just the total amount of energy that's coming out of this system that's hidden down in the center of the galaxy. So until recently, these kind of very nice artist conception was basically the best image that we had. So just earlier this year, we got our first actual image of a supermassive black hole that is eating material. And so here we can see this is in the nearby active galaxy M87. We have the shadow of the supermassive black hole, and then we have all the light that's being bent around it from this hot material that's falling into the supermassive black hole. And so this was produced with radio interferometry. Basically, you have telescopes all over the world that are taking data, and you kind of get a stereoscopic view from different points of view, and then you bring all the data together and you process it to get this final image. So this is one of the really big advancements in astronomy in the last year or two. As soon as this came out, some people tried to do some alternative processing to try to pull a little bit more information out. This is one of my favorites. Apparently the AGN and M87 really loves Winnie the Pooh. But that's enough of that. Let's get really serious now. So this is interesting, but why might we care on the larger scales of these galaxies? And the reason is that all this energy has to go somewhere. So this AGN is producing all this radiation, and it's traveling out into the galaxy, and it interacts with the gas and the dust in the galaxy. It excites it, it ionizes it, and then it can actually push it away from the supermassive black hole. And this is what we call mass outflows. So this radiation is traveling out, exciting the gas, and then blowing it away from the supermassive black hole. So this kind of process where the supermassive black hole is trying to eat and feed on material in the galaxy and then is injecting energy back into the galaxy is kind of known as feeding versus feedback. So the supermassive black hole is trying to eat material, but it's also pushing material away from it at the same time. So why this might be important for astronomy in general. So the first thing is looking at the evolution of the supermassive black hole and the galaxy itself. So as I just mentioned, you have material that's trying to work its way into the black hole, but all this radiation is also pushing material away. So as the supermassive black hole is trying to grow, it's actually simultaneously starving itself of the gas reservoir that it needs in order to grow larger. Related to that is star formation rates around the nucleus. So in general, if we have gas clouds, they can form stars as gas collapse down. If we're driving material out into the galaxy, then we can either compress gas and we can trigger star formation. It's called positive feedback. Or we can basically hit gas that would normally be forming stars, and we can disrupt it and we can prevent star formation, called negative feedback. Related to that then is enrichment of all the gas in the galaxy. So stars early on form lots of metals that are released in the center of the galaxy, and these winds, these mass outflows, can basically take those heavier elements and push them further out into the galaxy. And so that's going to change how your galaxy evolves over time. And so all of this is kind of tying into the formation of galaxies, the formation of structure. So this all sounds really good. Everyone's convinced, right? But of course the question is there evidence that this actually works? Is this actually what's going on in the galaxies that we observe? And so there are two really big pieces of evidence that lend credence to this. And so the first is black hole scaling relationships. So all we have here is basically the mass of the black hole versus the mass of the central bulge of the galaxy, of that kind of big semi-spherical distribution of stars. And this is something very similar. It's just looking at the velocity of those stars. And so what we see is that basically galaxies that have a larger bulge also have a larger supermassive black hole. Now, kind of first guess, you might say, well, that makes sense, right? Bigger galaxy, bigger black hole. But there's no necessity for it to be that way. And the reason I say that is that these are on very different gravitational scales. So even though supermassive black holes are these very massive, very dense objects, they only kind of gravitationally dominate a region that's maybe a few light years in size. Once you get past that, then basically the gravity of the galaxy is dominating. And so you have a supermassive black hole that dominates its immediate region, and then the bulge itself might be 1,000 times larger than that or even more. So they don't really know about each other right now. It's kind of like me holding a magnet at a paperclip a mile away. It's just the effect is too weak to really matter. And so the idea is that maybe this is an evolutionary process where basically the black hole and the galaxy kind of grew up together and evolved by exchanging energy and mass through this feeding and feedback process that establishes what we see today. So this is kind of on the smaller scales of galaxies. We can take this to the other extreme and look at simulations of basically the entire universe. And so here we have basically the distribution of matter in the universe, and on the right we have the temperature of that. And we're starting at a very early time, early in the universe, and moving towards the current day. So I'd like you to focus on the panel on your right, and that's the gas temperature. And what you notice is early on it's fairly cool, as shown by blue and green. And then as time goes on, you start to see these very discrete kind of little explosions of red, which is indicating that the gas is hot and it's moving away from these clusters of galaxies very rapidly. And so these are our active galaxies. These are our AGN. So hidden down in these simulations, we have our source of energy that is generating radiation and heating the gas up and pushing it out away from the galaxy. And so this is really important because if we don't include this in the simulations, if you basically turn it off, you get the wrong size distribution of galaxies. Basically, you end up with a lot of really big galaxies because we didn't have this effect to essentially tear them apart. And so we don't reproduce what the observations show us. So kind of tying this all together then, the question is feedback from outflows a working model that can explain what we observe? Does this actually work in practice? So that's a really big question. Let's take a slightly more bite-sized piece of that, which is, are the outflows actually powerful enough to produce this effect in order to affect the way that the supermassive black hole and the galaxy evolve, in order to push gas out of galaxies to produce what we see on the large scales? So in order to answer this, we need to very precisely quantify these outflows. So we need to measure how much mass is contained in them, we need to measure how fast they're moving, and we need to measure basically the energetics, how much energy is being carried by these outflows in order to determine if they can actually have a very significant impact. So the kind of the hinge to this is that this is very difficult to do accurately. It's very hard to determine the gas masses very precisely. And there's lots of different techniques for doing this, and they produce somewhat different answers. And so if you're trying to measure effect very precisely, one method says yes, the other method says no. We need to dig into this a little bit more. So these are kind of the big picture questions that I want you to keep in mind as we move forward. So in order to tackle this, we're going to use the two fundamental tools of astronomy, and those are spectroscopy and imaging. So first is imaging. So we're just taking our telescope and our camera, we're opening it up to the sky and we're letting the light come in, or we're passing it through some sort of filter that isolates the specific colors that we're interested in, and we're just getting a picture of what that galaxy looks like. So it tells us where different components are, it tells us how they're related. And then we can get significantly more information when we go ahead and do spectroscopy. So in that case, we're taking the light and we're spreading it out as a function of wavelength or as a function of color. And so on the bottom here, this is just a very basic example of a visual spectrum. So down here at the blue at short wavelengths, and down here at the red at long wavelengths, we just have all the different colors spread out and we can measure their intensity. So when we go ahead and do this for actual galaxies, we see kind of three main features. So the first one is what we call continuum emission. So this is just the underlying light at all levels from basically the stars and the gas and the dust in the galaxy. So if you just take the light from a light bulb, spread it out, make a spectrum, you'll get all sorts of different colors based on its temperature. Very similar here. We just have light at all the different colors based on the stars and the gas. Then after that, we have emission lines, which are coming from the excited gas. And so if you have gas, it's made up of individual atoms. And those atoms have electrons around them, and they can basically jump between very discrete energy levels. So rather than getting lots of colors, you get a very specific color at a very specific wavelength or a very specific color photon. And so that's shown by basically these spikes here. So we're getting extra light at very specific colors. And then the reason that this is so important is that because these give us a lot of detective clues that we can use to determine what's happening in this gas. So the first thing we can do is we can measure the velocity of this material, and that's through the Doppler effect. So if something is moving towards you, it gets compressed, and so in that case you end up with a blue shift, and so these lines will shift towards the blue end of the spectrum. And by reverse, if something is moving away from you, you get a red shift, and those lines will shift to the red. And so we can measure the amount of shift, and then we can determine the velocity of that material towards and away from us. And then on top of that, this can really help us constrain what's actually happening in this hot, excited outflow. And because each of these lines is coming from a very specific element in a very specific excited state, and so this lets us kind of lock down what the temperature is, what the density is, and ultimately determine how much material is in this outflow and how energetic it is, because that's what we're aiming for. So how this works in practice is we have a galaxy that we're interested in. We go ahead and we take the light and we isolate just a very specific part, so that way we can kind of know exactly what we're looking at. Then we take that light and spread it through a spectrograph to spread it out as a function of color, and then we record that on our camera, and then we can analyze it later. So let's go ahead and look at some of these data for some real galaxies. So the first two here, these are the new general catalog objects 4151 and 1068. And the reason I show these is because they're some of the most nearby, brightest active galaxies. And so they've been studied very extensively because they're brighter, they're easier to get high quality data on. So here we have the first piece of our data, which is the images, and we can see we have these nice, beautiful spiral arms that are filled with hot young stars and gas and dust, and then hidden somewhere down in the center is our AGN, the supermassive black hole that's eating all this material. So the next piece we can do then is go ahead and take a spectrum. So if we go ahead and isolate the light from some specific part of that and we spread it out as a function of wavelength, we get something that looks like this. So yes, this is not a Richter scale, this is not an earthquake, it's a spectrum. So starting down here, this is at the blue end, moving across to the red end. And again, we just see some of those few main features. So the first is continuum emission. So we're looking at, again, color versus the intensity of the light, the brightness of the light. And so we have an underlying amount of light at all wavelengths that's coming from the stars and the gas and the dust. And then from this hot, excited gas in this outflow, we have these very distinct, very pointy emission lines. And so I kind of want to highlight a few features of these that'll be important as we move forward. So the first is that we have two types of emission lines. So you'll notice that some of these are very, very narrow, and some of them are quite a bit broader. And so just like the shift of the line tells you about its velocity, the width of the line tells you about the range of velocities present. So basically, in the case of the broad lines, we have gas that's very turbulent, moving at a large range of different high velocities. And for the narrow lines, that gas is moving much more slowly, and so we don't get this spread in all the colors. In addition, we can go ahead and basically identify what is causing each of these lines. So all the labels specifically are not important, but basically we label each one by what is causing that line. So for example, hydrogen or helium or oxygen, and then its excited state. So I'll focus a lot on this one particular line, which we call O3, which is doubly ionized oxygen. So it's an oxygen atom with 2 electrons removed. And the reason that we focus on that one is basically because it's the strongest. And so it's the brightest. It gives us the best tracer of this really hot, excited gas in the galaxy. And so all of this has kind of led to a picture where some of these galaxies have broad lines and narrow lines, and other ones only have the narrow lines. And we're trying to understand why that happens. And the kind of unified model that has evolved is that this is basically just due to your viewpoint. So this is a little very simplified model, not to scale. It's kind of logarithmically spaced. And so down in the center, you have your supermassive black hole and your accretion disk of material swirling around it. That is putting out radiation, and that radiation will eventually hit some gas clouds. And in this case, those gas clouds are very close to the black hole, so they're moving much more rapidly, and so that gives rise to the broad line region. And then, so that's basically the point of view where we can see right down into the central engine. Now, depending on the way that the galaxy and the central AGN are oriented, you might also have a view where basically a lot of that structure is blocked. So you can't see this directly, and all you see is gas that's much further away, and then you just get the narrow lines. So that's kind of the overall picture that we have here. So now that everyone is up to speed on galaxies and spectroscopy and imaging, we can really go ahead and dive into the project at hand. So the problem to solve is we really eventually want to answer this question: are these outflows energetic enough to significantly affect galaxy evolution at some scale? But the difficulty there is that it's very hard to determine accurate gas masses. And so that's what my PhD project was about, was how can we determine the amount of gas in these hot outflows as accurately as we possibly can, or precisely. Now this is made even more difficult because this is what we call a multi-phase, multi-scale problem. So outflows exist in many phases, from very cold gas to hot gas to extremely hot gas, and you can't use one telescope to observe all of those. They just emit at different wavelengths. And so we're going to focus on one in particular, which is that narrow line region. So that region that's just producing those narrow emission lines. And so that is gas that's basically 1 parsec to 1,000 parsecs from the black hole. So that's about 3 to 3,000 light years. Those are the kind of scales that we're talking about here. And the reason that we're most interested in that is because it's the region of outflow that we can resolve closest to the black hole, all the way out to the scale of basically that galaxy bulge. And so it basically spans that full range. So if we're looking for something that's trading energy and mass, basically from the black hole to the bulge, that's the region that we want to focus on. So over here on the right is, again, that galaxy NGC 4151. So this is one of the most well-studied galaxies. Here's a very nice ground-based image of it. You can see it has some very faint, wispy spiral arms stretching very far out. And so this is an image from the ground. And so we can do very nice imaging from the ground. But if we go ahead and go to space and use the power of the Hubble Space Telescope, then we're able to get above the turbulent atmosphere and get very high spatial resolution. So if we go ahead and isolate this center portion here and zoom in and use the power of the Hubble Space Telescope, we get a very sharp image. And so we can see, again, these spiral dust arms. We can see there's a lot of very bright activity in the center. You can go ahead and, just like on TV shows, hit your magic enhance button one more time, and you get this image. So this absolutely blew me away when this was sent to me by Judy Schmidt. And so what you're seeing here is somewhere hidden down in the very center is this supermassive black hole, the accretion disk, the broadline region, all of that. And that's basically our energy source. That's what's putting out all this radiation into the galaxy. And that radiation is traveling out, and it's interacting with the gas that's within the galaxy. It's exciting it, it's lighting it up just like a neon sign, and then it's driving it away from the black hole at up to several thousand kilometers per second. So this is the image that I want you to keep in mind when we say outflows, mass outflows, excited gas. We have gas that's within the galaxy that's been excited, and now it's being pushed away from the supermassive black hole. So you can see it's very clumpy, it's very uneven, and so we really need to look at this in great detail at high spatial resolution. So again, our goal here is to go ahead and measure this as precisely as we can. So we're going to focus on very nearby galaxies. They don't necessarily have very powerful AGN or very, very powerful outflows, but we can resolve them in very great detail, and so we can learn about the physics of what's going on. We're going to go ahead and use our spectra and imaging that I'll talk about to model these to determine the mass, and then ultimately we want to compare with what's been done before. We want to see if we actually did any better, if we can see where things disagree or agree. So the way that we're going to do this, first we want to go ahead and figure out how much material is in this outflow. We want to determine its mass. We want to go ahead and determine its velocity, how fast it's moving, and then R, which is basically just how far it extends out into the galaxy.
Supermassive black hole in galaxy M87 was about 6.4 billion solar masses. Is that correct?
I believe it's in that ballpark. I'd have to double check. Yeah, it's quite massive.
And so, what is the estimated mass of the supermassive black hole at the center of our galaxy?
It's significantly less. So it turns out that even that's in a very more further away galaxy from us, they have about the same size on the sky. So it's much less massive, but it's much closer. So you can get about the same images of it. Yeah. Are we all set, Jim?
Hold on one second.
Yep, take your time.
Is the black hole in our galaxy not doing anything?
The black hole in our galaxy is quite inactive. Yeah, it's a very quiescent galaxy.
What does it do? It must do something.
It sits around a lot. Yeah, yeah, it hangs out.
It had to be active at some point, would you say?
Absolutely, yes. And so
It had to
there's
be active.
so the idea is that eventually all galaxies will go through this phase at some point
Oh,
during their
that's
evolution.
important.
And so yes, the idea is the Milky Way was active much further in the past, and there's kind of some remnants of that, but it hasn't been active any time in the last thousands, tens of thousands of years. Yeah.
So what's next for supermassive black hole? I mean,
What's next
Oh,
for inactive black hole? What's gonna happen?
It'll essentially just sit there, not doing anything unless material gets close to it. So that either comes in the form of gas that's worked its way towards it, another galaxy, or often a star that gets too close. In that case, the star will be ripped apart. It'll be ripped apart and give it gas.
That it started a jet?
Yeah, so there's evidence that you could see material being ejected that had been ejected a long time ago. And so it's at much lower energies.
Not that gas that just went by.
No, that was slightly different, yeah.
But it just kind of questions like we were talking about using the Hubble Space Telescope to get the increased resolution.
Mhm.
But I thought in some ways using like some of the new techniques to I thought the resolution of some of the Earth-based telescope had been pretty close
With
to
adaptive
Hubble.
optics.
Yeah.
So the question being, can we basically do as well as Hubble from the ground? And so now we almost can. We can use adaptive optics that basically change the shape of the mirror to try to account for the fact that the atmosphere is turbulent. So you can get about the same level of detail, but those corrections aren't perfect, and so the light still gets smeared out a little bit more than you would from space.
One of the things I've come across in my readings is the black hole seems to dictate some form of galactic structure. What about irregular galaxies that don't seem to have any structure? Yet, like Bo's galaxy, there's obviously some form of an outflow from that thing.
Yeah. That's a good. So in general, these kind of relationships we see apply to kind of well-formed, well-behaved galaxies. In general, irregular galaxies, which a lot of them kind of look like train wrecks, they're galaxies that are either being torn apart or they're very small. So either they generally don't have a supermassive black hole, or it doesn't. They don't relate necessarily to one another. And so you can imagine if you have a large galaxy and a chunk of it kind of gets torn off over time, then it's not going to line up
That's
anymore.
why the spirals are good to study. 'Cause
It kind of gives you a very clean control
Right,
sample to
something to
start
start
with.
measuring.
Exactly. All set? Great. All right, good questions. So, yes, so let's dive back in. So yes, so we want to go ahead and determine the amount of material that's in these outflows, how fast it's moving, and that's going to let us calculate a couple different quantities. The first one is the mass outflow rate, and so this is basically if you are standing at some distance from the supermassive black hole and you measure the amount of material that's sweeping by you, it's exactly that. It's just like the flow rate through a fire hose. In this case, we measure it in solar masses per year. So we're just measuring the amount of gas that's being swept away from the supermassive black hole. And then related to that are a variety of energetics. So this could be the momentum or the kinetic energy. It's something that's related to the velocity because we can have a lot of material moving very slowly or a lot of material moving very quickly, and that's going to change how strongly it's able to impact the galaxy and structure beyond the galaxy. So all of this kind of comes in two flavors. And so the first one is what we call integrated measurements. So this is basically you take everything within some radius and you just add it all together and you use a single mass and a single velocity and you calculate everything based on that. The other way is to do it spatially resolved. So we actually go ahead and split this up into smaller and smaller zones, and then we can measure these properties as they change. So we can basically track and see if we have more or less mass, if it's moving more quickly or more slowly as we move away from the supermassive black hole. And then as I'll highlight later, there's lots of different ways for determining what the mass is. So we're going to go ahead and do it what we think is the most precise way we can, and then we'll compare it with some of those techniques. So with this, we're going to need some data. And as I alluded to before, a lot of this is going to come from the Hubble Space Telescope. And so the reason is that, again, we get very high spatial resolution. We're able to isolate very small portions of the galaxy on the sky, and so we can measure how things are changing across the galaxy. And then following up with that, we also have some observations from the Apache Point Observatory, which is, here's a 3.5 meter telescope there. This little tiny line is a person for scale. So I was fortunate enough to get to go out there a few times and obtain some supplementary observations. And so the nice thing here is we can't necessarily get that really sharp view, but we can trace very faint emission very far out into the galaxy because we can observe for a very, very long time. And so we can basically piece these two things together. We have the Hubble data that gives us this very high precision view of the center of the galaxy, and then we have these ground-based observations that kind of let us look at what's happening on larger scales. So we have our observatories. We're going to need a sample. We're going to need galaxies to look at. And so all these galaxies come from previous work by another PhD student, Travis Fisher, who basically tried to identify galaxies with these strong outflows. And so I'll be highlighting 3 in particular that were the ones I focused on most for my PhD. And so these numbers up here, the key point to take away is that as we go from left to right, you're going from very close galaxies to further away galaxies. And you're going from low luminosity, weaker AGN to more powerful, more luminous AGN. So we're able to kind of look at how these things change over a range of parameter space. So this is our entire analysis in a nutshell in one slide, and then I'll kind of walk through it with some more visuals. So the first thing we're going to do, here's an example of that second galaxy, looking at a particular wavelength of light. And so we can see this hot, excited gas here, along with some of those spiral structures from before. And we're going to go ahead and take our Hubble Space Telescope spectrum, and we're going to get an individual spectrum at each location along the galaxy. Then what we're going to do is we're going to go ahead and use that, and we're going to look at where those emission lines are, and we're going to use that to figure out the velocity of the material. And then once we have that, we'll use all the other emission lines in the spectrum to create a model to determine how much mass is there. Once we've done that, that's going to give us the mass at each location along this little slit. But if you remember from the image before, that basically blocks everything else out. And so there's a lot of material that's out here outside of what we're able to see. And so we're able to go ahead and basically use the models to do a conversion from the spectra to the imaging. So we say, okay, based on the amount of light I see in this spectrum, that gives me this amount of mass. That lets me get a conversion factor that I can then use to figure out the total mass at each distance, basically by making these little concentric annuli from the image. And then finally, that'll allow us to calculate these quantities, the mass outflow rates, the energetics. So let's go ahead and kind of walk through this to get to the main result. So the first thing is we're going to go ahead and extract a spectrum. This is an example of one just near the center of the galaxy. And so again, we're going from blue to red. And the takeaway point here is that we have a wide range of emission lines from lots of different ionized species. So we have neutral lines, which basically means the gas is very calm. It's not very high temperature. And then we have things like iron 10 and iron 14, which have lots and lots of electrons ripped off. And that requires very high temperatures, very harsh environment. And so this is all basically coming from the same region. And so we need to account for all of this in order to accurately determine the gas masses as best as we possibly can. So again, here's those strong oxygen 3 lines. We go ahead and we make fits to them. And in this case, we actually have 2 of those lines. And so this indicates that we're seeing gas that's just rotating slowly around the galaxy. And then we also have gas, in this case, redshifted, which I've colored blue because why not, that is moving at much higher velocity, and that is part of the outflow. So you have a chunk of gas that's rotating and a chunk of gas that's outflowing at several thousand kilometers per second. We go ahead and we do this at each point along the galaxy, and what we get are these curves. So here we're looking at about out to 5,000 light years into the galaxy. So right here is the center of the galaxy in each one of these, and then this is looking at the gas velocity. And so what you see is near the center, the velocity is low, and then the velocity rises to some peak value, and then it decreases again, and then it just kind of calmly turns over into what we would just think of as normal rotation, which is given by these kind of quasi-red lines here. So again, what we're seeing is that the velocity of the gas is increasing and increasing out to some distance, and then it's decreasing after that. And there's a couple of reasons why that might be. So this gives us that first half of what we need. We needed the velocity, now we need the mass. And so this is kind of the key to our process. This is what we hope to think makes our process unique and allows us to determine the gas mass as accurately as we can. So we're using a computer code called Cloudy. Very creative name. It's absolutely fantastic code that's been developed over the past, say, 40 years, so it's very well tested, it's very well expanded. And what we're going to do is we're going to make models that include different conditions. So rather than just saying all the gas is at one density or one excitation state, we're going to allow for a range of conditions in order to produce all those different emission lines that we saw on the spectrum. So what we put into this, we basically have to put into the model the radiation that's coming from this central active galaxy. We have to go ahead and tell it what kind of gas it's looking at, and so we use the spectra to determine basically the abundances of the gas, how many metals are in there, how many elements of oxygen, nitrogen, so on. Basically figure out what the distribution of the gas is, anything else that might be in the gas, for example, dust. And all of this is important because it'll change the heating and the cooling within the gas, and it'll change the spectra, and so you might get a mass that's not correct if you don't account for all these things. So this is one of only just a few equations, and the key point here, U is just the ionization parameter, which is basically the level of excitation of the gas, so a bigger U means the gas is more excited, and that's the number of photons hitting the gas divided by basically the number of atoms at that distance. And so if you have more light hitting the gas, you can get it more excited, you can produce more highly ionized lines, and vice versa. And since these galaxies are spatially resolved, we basically know all of the numbers that go into this except for the density of the gas. So you say, okay, in order to reproduce this spectrum, I think I need a particular density. That means the other parameters are locked and they have to vary together. So rather than just kind of searching all these different parameters, we have something that's very well constrained because we're able to see where that gas is. So finally, what we do then is to go ahead and compare what the model predicts with what the data give us, and then we see if we find a match. So this is an example of that. Basically, what you're looking at here is all those different emission lines in the spectrum, and you're looking at the model over basically the data. And so if it were to pass straight through this line at 1, that would be a perfect match. And then these blue lines here indicate a factor of 3 agreement, and you can see everything is within that. And of course, all of our fits look exactly this good. No, so there are cases where things disagree, and sometimes that teaches us something and we have to change the model, and other times it agrees really well and we can move forward from there. So what this eventually gets us is it lets us predict all the parameters that give us the gas mass. And so these are the last equations, promise. So what we have here again is we have this image of our galaxy, and we have our slit here from our spectrum. And what the model tells us is how much light should be coming from that gas based on how excited it is, which is its flux. We know how bright it appears to be, we know how far away it is, so we have a total luminosity. And so that ratio basically tells us the area of all these clouds. And then from the area, the model also predicts the number of particles that we're looking through. That gives us the total mass of that gas cloud. So then from there, once we have the mass at each location along the slit, we set up this scale factor that basically says, given the amount of mass I see and the luminosity that I see, what is the ratio between those? So for every photon I get, how much mass has to be there? And then we can use that with this image of the galaxy. We can measure the brightness at each distance, and that lets us calculate what the total mass is at each of those distances. So with that, I'll just go ahead and jump into the result. So what we see here is we're looking at distance from the center of the galaxy, and on the left is the mass, and on the right is the mass outflow rate. And so for the first galaxy, NGC 4151, that's the lower luminosity galaxy that's much closer. It's down here in gray. And so you can see it just basically reaches out to about 150 parsecs, or about 500 light years, and then that's basically it. There's just not enough energy to excite the gas and drive it. And then we can see for our next galaxy here in blue and orange, which is just stitching together our Hubble Space Telescope and our ground-based data sets, we have a lot more mass and it reaches a lot further into the galaxy. And so in this case, what we see is that basically right at the center, the mass is just kind of sitting there, it's not doing much, and then it increases in velocity up to a maximum rate of about 3 solar masses per year. So that means if you were standing at that point and you measured it, you would see basically 3 solar masses worth of gas every year rushing by you, and then it decreases back down to 0. So these are the results for the first two. If we add in the third one, it gets a little more complex because not all of the gas is outflowing, so it looks like some of the gas is rotating around the galaxy and other portions of the gas are being blown out. And so that's what's shown in red and blue. Basically, if you assume that everything is moving away, you would tend to overestimate how much gas is actually in the outflow. You would overestimate its impact on the galaxy. So you can also do this. You can look at a range of energetics and things. So if I just summarize briefly here, the range here is only about a factor of 4, and yet these galaxies have very different AGN powers. So we might expect that to be somewhat bigger. And so where we see that difference is when we look at the energy. And in this case, here's the first galaxy right down here, right at the bottom. And so the reason we see this separation is because now we're looking at the energy, which depends on the velocity of this material. So the material is moving more quickly, there's a lot more of it, and so it has a lot more energetic impact that it can then go ahead and impart to the galaxy. So that's a lot of material. Anyone overwhelmed? Just a little bit? Okay, perfect. So let's summarize. Let's summarize what this tells us so far. So what we're seeing is that the amount of gas in these outflows, how fast it's moving, and how far it reaches into the galaxy is linked to the power of our AGN. So that kind of makes sense. The more energy that we pump into the galaxy, the more gas we can excite, the more quickly we can drive it, and the further it can reach out into the galaxy. So that seems good so far. The question then is, how does this compare with other techniques that have been used before? So I spent a couple years doing all this for a few galaxies. Was it worthwhile? Did we actually really learn anything in particular? And so I'll compare with two types of studies. The first is those unresolved studies where we basically just lump everything together and use a single measurement of how powerful these outflows are, and then look at some other ways of estimating the amount of mass that's in these outflows. So the first one is if we go ahead and basically just add up all the gas we see and we assign it a single number. And so what it does, you essentially look at how much gas you see, you pick a particular density for it, which for us is coming from models. In this case, it might be coming either from kind of just a close guess or some information that you can get from the spectrum. And what we see is that we get a mass outflow rate of 65 to 6,500 solar masses per year. That's a lot. So it's about a factor of 1,000 or more bigger than the answer that we found. And what we think this happens is it basically comes down to the fact that a lot of these parameters are very uncertain. You're basically basing the amount of mass on how the galaxy looks rather than using a tracer of how much material is actually there. So another way of doing this is similar to our process, but we're basically looking at a single emission line. So rather than looking at all these different emission lines and creating all these different models, we're just going to pick a single emission line, pick a single density, a single velocity, and use that to get our mass. And in that case, the answer actually agrees pretty well. It agrees within about a factor of 2 to 10. So depending on what you're doing and what kind of data you have, that might be the way to go. So in this case, we want to go ahead and basically use what we call luminosity-based methods that are using spectra and imaging rather than basically just using the imaging by itself. So the question then, the final question is, can we go ahead and do this without doing this very complex modeling process? So by making all these models, we think we've got a very accurate answer, but it takes a lot of time, it requires a lot of data, and so we can't do this for a very, very large number of galaxies. So we want to go ahead and see basically, is there somewhere that we can simplify this process? Is there somewhere where we can trim this down? And so if we just have a single spectrum of a single line, that will tell us about the velocity of that gas from its shift. It'll tell us about how far it reaches out into the galaxy, and it'll also tell us about basically the brightness of that gas. So then the question is, all we need to do is just know the density of the gas, because that tells us about how efficiently it emits. It tells us how much light we get per unit mass. So there's a couple different ways to do this. I'm just going to highlight two. So the first one is to use emission lines in the spectrum that are sensitive to the density. So there are certain emission lines that will change their strengths based on the density of the gas. And so in this case, those are sulfur 2. And so just to show those results briefly, basically down here in gray is the result that we got from our models. And in blue is the result that you get if you assume the density by using this proxy in the spectrum. And so in this case, you can see it overestimates at some places by about a factor of 6 to 7. Now, depending on what your goals are, that might not actually be that bad. This took significantly less time, it took a lot less data, and so you can do it for a larger number of objects. So it's promising, but it doesn't show really great agreement. The other common technique is to just pick a density based on what other galaxies look like. And so a very common value is just 100 particles in each little unit of volume. And so in this case, you actually can't see our result. It's way down here at the bottom. So if I zoom in on that, our result is down here. And the result of that assumption actually goes way off the chart here. And so it overestimates compared to what we got by about a factor of 60. So that's a pretty large disagreement. Now, this is one of the worst cases. There are some cases that are better. And so with just a few galaxies, we can't really make a very concrete claim yet as to whether this works. We need to look at a few more galaxies. So to summarize this portion here, if we go ahead and just add everything together, it gives us a very uncertain answer. We need to actually look at how these properties are changing as a function of distance into the galaxy. If we go ahead and actually use images and spectra, that gives us a better picture than if we just go ahead and try to estimate the gas mass from the images alone. And if we use some of the common assumptions that are used in the literature, we actually get the largest disagreement. So that's somewhat concerning. So the future work for this then, Ultimately, we want to do this for a large number of galaxies. We want to span a big range of parameters. We want to look at how this changes with different mass black holes, with different AGN power, things like that. And then we want to go ahead and look at galaxies that are much further away that have much more powerful outflows. So with that, we'll go ahead and conclude. So what we're finding is initially is what we expected, so that as we have more and more powerful AGN, we're able to drive more powerful outflows to larger distances into the galaxies. We find that basically the mass outflow rates are about 3 to 12 solar masses per year, and so over some amount of time, this might be sufficient to basically clear the inner bulge of gas and affect the way that the system evolves. If we go ahead and add everything together, we get a very highly uncertain answer. And if we go ahead and use some of the assumptions that are commonly used, we actually get the largest disagreement. So we need to look at that in much greater detail. And then finally, we feel that this modeling process is necessary if we want to get the most precise answer that we can. And eventually, we're going to go ahead and extend this, looking at more galaxies over a wider range of parameters using a whole bunch of different observatories. So with that, I would be happy to field any questions. I know they wanted to pause just for one moment.
So I just want to ask, the sulfur 2 and the O3, is the density of that would be higher towards the center of a galaxy?
Yeah, so that's a good question. The question is basically, is the density change as we move out? And so I didn't have time to touch on that as much as I like. So yes, that's exactly right. Usually the density is higher when we're close to the AGN, and then it gets lower and lower density as we move away. It's not always the case. There's some fluctuations on top of that because this material is very, very chunky, very inhomogeneous. But in general, yeah, it tends to decrease as you move away.
Does that go into the equation, or that's just, it's not really a non-factor?
No, it does go in because what happens is the reason that we get such large disagreement with some of these techniques that have been used before is as the gas gets more dense, it emits more efficiently. You're able to get photons out faster. And so the densest material is producing most of the light, but it actually has the least amount of mass because you don't need very much of it because it's emitting a lot of light very efficiently as compared to the material further out. And so yes, that definitely factors in. We're definitely looking at the density at each location rather than just picking a constant value.
Okay, thank you.
Who's next?
Hi, Mitch. I noticed that, well, the excitation equation that you showed there, it looked like it was isotropic, and I was just wondering if there is some kind of axial anisotropy in these nuclei and the areas around them.
Yes.
Wouldn't it be important to take that into consideration when you're doing this?
Absolutely. That's a great question that kind of swept under the rug. So the question is, we're modeling everything in this very narrow slit and then assuming that that applies basically to everywhere else in the image. And so that's a very good question because this structure is very clearly inhomogeneous. It's not always very symmetric. And so what we do is we make the models based on what we see in the slit, and then we try to pull as much information as we can to check if that's valid outside the slit. So for example, with our follow-up ground-based observations, we can't isolate it in as great a detail, but we can at least check that, for example, the velocity of the gas is very similar. And for the regions that are furthest outside the slit, that may not hold, but it tends to have very, very low flux, very, very low mass, and so it's not making a significant contribution. So yeah, there's definitely uncertainties in there of the order of, say, 20% or something like that.
Anyone else?
Just top all of
Hold it right in front.
It's recording on amplified.
Just, does this gas reach galactic escape velocity? Does the galaxy actually lose mass here? Or is it perhaps captured by the globular cluster halo around the galaxy?
Right, yeah, so the question is, does this material actually get fast enough to escape the galaxy, or can it essentially be pulled back in? And so for these nearby galaxies that are not particularly powerful, in general, our modeling suggests that the material will ultimately either fall back in or kind of reach a distance and then kind of peter out. But what we see is that as long as these trends continue, as you go to more powerful AGN at larger distances, that material should be able to escape the galaxy. And we do see observations that support that, where material is basically blown outside the galaxy and is starting to interact with nearby galaxies. So be happy to take another question or two if there are any, and we could also go ahead and cut it there. And
some more
oh, okay, great. Yeah.
Sorry, I didn't realize you only had a few questions asked, but what I was actually getting at in my previous question is that rather than heterogeneity, there might actually be an axial structure that you could compensate for with the equations. So in other words,
So because of the 3D geometry?
right, well, you were looking at galaxies that were on edge and face on, and you would think that if there's some axial anisotropy in there, that you would get a very different answer looking at a face-on galaxy. That's kind of what I was getting at. With
Yeah,
that.
no, okay, yeah, I think I'm following you better. Yeah. So all the velocities of this material that we see are all just kind of in projection. So if the material is not moving directly towards you, you'll measure a different velocity than it's moving kind of across your line of sight. And so we do model the galaxy itself to determine basically what its inclination is, and then we use that to correct for the projection effects. So if you're only seeing a piece of the velocity rather than the full velocity vector, we use that to go ahead and basically deproject it to its full value. I think oh, yes, sorry.
Hi, Victor Payne here. I have two questions. The first is when you take the spectroscopy of the gases, do you take into consideration the overall galaxies, red or blue shift? And secondly, are you also taking into consideration the Fermi bubbles and outflow coming from the top?
Right. Yeah, so the question is essentially, these emission lines track the velocity of the gas, but it tracks all the velocities. And so if the entire galaxy is also moving away from you, basically the things add up. It's kind of, you're standing on a cruise ship and you throw a baseball forward, the velocities stack together in some way. And so yes, the way we do that is we look at the absorption lines from the stars, and that tells us basically what the bulk velocity of the entire galaxy is towards or away from us, and we subtract that off our spectrum. Then we go ahead and measure the velocities from there. In this case, these galaxies are still active, and so in relation to the Fermi bubbles, so for the Milky Way galaxy, our own galaxy, when it was active, it removed some of this material, and there's still kind of these echoes, what they call Fermi bubbles. They've been discovered using the Fermi mission. And so in these cases, we don't necessarily see those because they're still in the process of pushing material out. So we don't see kind of those older echoes. But it's not impossible, depending on which portion of the spectrum you look in with different telescopes, they may be present in some of these galaxies. They do kind of stack up.
Your methodology, is it useful for other than spiral galaxies?
Yes. So in general, the methodology itself should be able to apply to any galaxy.
Okay, globulars, whatever.
Yeah, it should apply to ellipticals and irregulars and things like that. The key is that you need to roughly know where this gas is in order to determine what its true velocity is. And so if you have kind of just a spherical galaxy and the gas is, it could really be, you could be...
And no black hole.
Exactly, yeah. And so in theory it applies to anything, but in these cases we like the spirals because we can model the disk and get a frame of reference as to where it is. So I'll be around for quite a while after the talk. I'd be happy to take more questions, but I do...
question
Oh, please do, please do.
Maybe not the last one, but my question is, with the models that you're using, is there any consideration to dark matter at all?
I knew it was coming. Yes. So essentially, in all these galaxies, most of the matter that we see should probably only make up a small fraction of it. There should also be a dark matter halo, for example. So in terms of modeling the gas, that doesn't come into effect. Where it does come into effect is if you're interested in understanding whether or not this gas can actually escape the galaxy. Well, as the gas is moving out, you're encompassing more and more mass in the galaxy, and if there's a heavy dark matter halo there, it's going to be able to slow that gas down much more efficiently. So again, for the galaxies we're looking at, I don't think it really reaches the scales where we could be able to disentangle that. But yes, it does absolutely play a role.
Thank you. Any others?
Do you still go out and observe?
Oh yes, absolutely, absolutely yes.
Is that allowed?
Of course, yeah. Yes, I still have a few telescopes, including some I built during my time here. I love nothing more than to actually go out and look at the moon, look at Saturn. A lot of folks in astronomy consider the moon to be light pollution. I think it's absolutely one of the most fascinating things to look at. So yes, I absolutely do still get out and observe. Yes.
Okay. One more?
Have we ever determined yet, have we actually isolated dark matter or dark energy?
No.
We have not.
I'm just there are some folks that would debate that very heavily, but since we're not recording anymore, I can just say no. Yeah. So thank you so much again, everyone. I'll be sticking around for a while. If you have more questions, please come chat with me. Okay.
Okay, thank you, great questions. The NJAA Club would just love to congratulate you on your retirement, Teri. And thank you so much for your donation that you helped raise for our funds. Everybody in the club appreciates sincerely the dedication that you've given to us over the years, way before I've been here. Thank you again, and we hope that the next time you're up our way that you always try to stop by with the website. Thank you. One more thing before you go. This is as hard for me as it is for you. The club really, really feels proud that we brought this fine young guy to a point that he is. It's not all our doing, as a lot of you can attest to that, but we do appreciate it, and you're always welcome. Hang this on your wall.
Thank you very much. Thank you. Appreciate it. Get in here.
Tilt the flag towards me just a little bit. There you go. Get the reflection.
What's that?
Tell everybody what it is.
Oh, I'm sorry.
Jim's demand.
Do the photo first.
One more. Thank you.
Okay, I should have mentioned, it's an honorary lifetime membership award, which is few and far between, but we do appreciate the effort that you've put into astronomy, and as a club that our main mission since the inception of the club in the 60s has always been outreach. Exactly.
Thank you very much.